Now, in order to see the real impact of indexes, let's do some experiments in an actual SQL database. So here I am in this perfdemo database where I have a table that's much larger than we're used to dealing with. So the size of the table will let us see the impact of indexes more clearly. So let's see what we have. I just have a students table, kind of like from an LMS. Let's describe it. So I have UID, date of birth, and major, and UID is the primary key. So we should already have an index on UID, so we could do quick searches filtering by UID. Let's see what we have in here though. First, let's just count the number of rows. So select count from students. And we have 1.8 million student records. So kind of starting to approach a more realistic database size. All of the little demo tables we've been dealing with throughout the semester are tiny, and this is a little more realistic. And we can even see that just counting the rows took a quarter of a second, where we're used to queries, even select queries, being reported as something like 0.00 seconds, where it's not actually 0, but it's less time than can be displayed in this many digits of precision. So let's see what the format is in this data. So let's select star from students, but I'm not going to get all of the rows, so let's just limit to 20 just to see a few of them. So I have increasing UIDs starting at 0 and going up to 1.8 million minus 1. And then every student has a random date of birth going back 2,000 years. And that's just to give a very large number of possible dates of birth so that we don't get too many students with duplicate dates of birth. There will be some duplicate dates of birth, but I wanted to spread them out much more. And then every student just has a random major picked between art, CS, or math. So all of them are going to be one of those 3 majors. Okay, so let's see, let's verify that we do actually have an index on UID since it's the primary key. So we can do show index from students. And this gives just a report about all of the indexes on the table. And it's wrapped around, so it's formatted a little poorly, but so we can see here is the index name, primary index. So we do always get the primary index, and it is indeed on the UID column. And this one here is the index type. So it's reported as a B tree. It's actually a B plus tree. InnoDB does use B plus trees. It just uses the term B tree. That's kind of it's old and kind of left over from previous days. All tree indexes in InnoDB though are B plus trees, not B trees. Okay, so let's do some queries. Since we have this primary index on UID, we should be able to quickly filter by UID. So let's do select star from students where UID equals, so we'll just look for an exact match. I'll just pick any UID between 0 and 1.8 million. So I don't know, just kind of make something up there. Let's see. Oh, got to spell students right. Students. Okay. Run it again. So we can see that we can find a student by a particular UID in very close to 0 seconds. I ran it twice, and it's some very small number that sometimes cannot be reported in this many digits of precision. I can find one record out of 1.8 million very, very fast because of that index. Let's try the same thing, but let's search for a particular date of birth. So where date of birth equals, and then we'll just pick a date. Let's do 1900, January 5th. and it took, 0.4 seconds, close to half a second. So something like 41 times slower, at least 41 times slower than searching by UID. And I picked one. I already knew this date. I happen to know that there's only one student with that birthday because I wanted to be fair in comparing. This query only returned one row, so I wanted this query to only return one row. But since there's no index on date of birth, it takes a very long time, relatively, to find that one student with that date of birth. But if we want to search by date of birth and find all students with a certain date of birth, then we should be able to create an index on the date of birth column. So let's create index. I'll call it date of birth index on students date of birth column. And we can see it's taking a few seconds to run, so 3.38 seconds to build that index, because it has to take all 1.8 million of those dates of birth and put them into a big B+ tree. So now let's run that same query where I'm searching for students with a particular birth date, and there we go. We can do it in very little time. On par with searching by UID, since we now have an index on this column. Now let me change this query to do greater than that date. So find all people with a birthday greater than that. And it takes 0.19 seconds. So it looked like it took longer than that, but that was just printing all of this information. The time reported is just the time to process the query. So about 0.19 seconds to find all students, lots of students here, 100,000 of them. But that's even less time than it took to find a single student before I had the index. It's still taking, this is almost a quarter of a second, still quite a bit of time, and that's just because once it finds the first student with this birth date, then it still just has to kind of march forward and visit every other remaining page. But still impressive is that it's faster than finding just a single student if there was no index. Okay, so let's try something else now. We want to find all students where the date of birth is greater than that date, and let me just clear that, and where their major is art. So this should be fewer students returned, but let's see how long it takes. Okay, so far fewer rows found, but took the same amount of time. And that's because there's no index that's going to help with the major part. We can still use the date of birth index, but then we still just have to kind of step through all of the students with a date of birth greater than that date and find the ones that have this major. But if this is the kind of query you want to do involving the date of birth column and the major column, then we can add an index that incorporates both of those columns. So let's create index, I'll call it date of birth major index on students, and then I'll put both of those columns into the index, date of birth and major. So this is not two indexes, this is one compound index where the search key includes both of these things. So that will take a few seconds to build, and then let's try our query again. So same number of rows returned, but in a fraction of the time. And this time savings is even more than you might expect. And here's why. So before I added that two-column index, all I had was an index on the date of birth column and the primary index. But remember, the index on the date of birth column is a secondary index, so it only contains these search keys and the primary key. It does not contain the major. So we can use that index to quickly find all of the students with a birth date greater than some date. But then if we want to know which ones of them are art majors, we have to go use the primary key to look up the full row in the primary index and then compare their major to art in order to filter them out. With this index that I just added, date of birth and major are right there in the search key. So I can look at the date of birth and the major right here without ever having to load the full row out of the primary index. And I can filter out all of the art majors just via these search keys and never have to load those full rows that don't match.